many people today in here? Spring is coming. Everybody gets excited about, good days. In Boston we have a long winter, so it's so fun. Spring comes, summer, right? Bingu here will come later and give us a demo on support vector machines optimization, right?
Yes.
So we'll talk for about an hour, and then he'll come in and show us his implementation of SMO. So today, I think I'm doing much better in terms of schedule than you guys actually. As in if I look at where I am with the lectures, right? And if I look at where you are with the homeworks, that's some big gap in there. Right? You guys gonna catch up? I mean, I'm doing support vector machines right now, right? I'm about to finish support vector machines. There's a homework on support vector machines. I made it significantly easier for undergrads because undergrads do not have to implement SMO, but the grad students do. So that being said, we'll have another topic after support vector machine. I'm going to talk about similarity functions and k-nearest neighbors, which many courses do it in the beginning. I choose to do it at the end because I want to have some supporting ideas for KNN. So that's why we're going to do it, probably next week. And I think there's a week after that too. How many weeks more do we have? This week is the next week, and then I believe there's another week of classes. So we kind of have almost an additional time in here. Like the last week, we could talk about fancy things like recommendation systems or reinforcement learning or clustering. You guys can take a pick what you want to see, and we can talk more about those things. I can show you some super fancy stuff that is not even machine learning curriculum. What's that?
Like what?
There's this heat equation that talks about equilibrium and how to realize equilibrium, how to make out of it a machine learning algorithm, for example. There's ranking problems. So as I said, I'm ahead of you guys. And you should focus on finishing the homeworks, which is homework, the features, right? The homework 6, I believe, and then the support vector machines, and there will be a local classification homework, which is the KNN idea. Which, because we do it at the end, will not be as simple as you remember KNN from the past. Just pick the closest neighbors and that's it. We'll make it a little bit more complicated and more useful. So, few logistics. If we have to, we can skip a class, make it office hours, but I don't think that's that useful. We have plenty of office hours. I think it's useful to just keep talking about interesting things, even though some of these things will not be in your homework. So logistics, exam, 4:20, 10 a.m. I know you know that already. And then I can't make a class that is next week on Thursday. So Thursday, 11? So that's next week.
You're right. 16, right?
Correct. So here, I can't be here. I have to be out of town. My plan is to keep that class, to have it, to be a guest lecturer, which is a spectacular professor. You're going to have Javeda's lunch. So it's pretty rare to have him anymore because he has a lot of administrative dean duties, and so on and so forth. But he'll give you a class. We'll record it, of course. And he's a spectacular teacher, teaching the words and such. So you'll have fun. So that being said, another thing is homeworks have to be due sometimes on 22. I will talk to the TAs about that. to make sure everything works. As long as we can put the grades, it's fine. So I don't have a hard deadline on 22, but to make it fair, don't push it towards the last moment. We don't want on 21 and 22 to get everybody demoing 3 homeworks. Okay? So priorities will be given at that point to homework 7 and 8. If we have time, we'll do the back homeworks too, but just plan accordingly towards the end to have only 1 or 2 homeworks. Also, during that time, we got to talk about your exams. So after you do the exams on the 20th, we'll look at it, we'll have an initial evaluation with clear things that you've done and clear things that you're missing. But then you'll have the chance to go with me or the TAs over the exams and say, okay, you missed my function that did that thing. Okay, if it's there, we say, we'll also tell you what we think you missed and what should have been done, so on and so forth. So I want to have at least one day where people can talk about the exams just like we talk about the homeworks. So now, where are we? We got to finish support vector machines, so we got to do 2 things. Let me write the story and get it here. I would really like you guys to remember this picture. So I'm going to draw it a 3rd time. This was the margin. This is the let's say the plus side. So we did some calculations here. I'm not going to repeat the calculations. We have a separating plane. We have a bunch of plus points and a bunch of minus points. And we said the closest points, the plus and the minus, we set them by scaling at +1 and -1. Assuming this is in the middle, we can set this to 100 and -100 if we want to. But by zooming in and out, we set this at +1 and -1. So we want the closest pluses to be at +1, the closest minuses to be at -1. Under that setup, we calculated the margin, what it did was a little bit of geometry there with parallel lines, and the normal on the plane is W. So we did some simple arithmetics and we got this point. And then we said the primal problem is, let me write the last version directly. Here, we want to minimize so this is saying minimize this means maximizing this margin, which is rotating the plane to be in the most equilibrium position. But then we introduce these errors or slack variables. So the slack variable is admitting the reality, which is we can't really have a nice separating plane that all the points are exactly at +1, -1. That's ideal, that's what we want. But in practice, we may have some plus that's in here. And because it's only 1 point, we don't want to lower the margin here. We'd rather have the margin here and say, this is like a slack here. This is like the how much that point went inside the margin. Of course, I can have a point that's way over here, a plus, and then the slack or the error for that point must be a bigger one, right? And I can have the same for minuses. I can have a minus over here. So if this is a minus point, then because it's not allowed in theory to go inside the margin, the slack variable will be this. So the slack or error variables are how much I allow all the points together to violate the margin idea. So every data point gets this slack variable, zeta I, which is, if it's not violating anything, it's 0. So if it's on the right side of the margin, I don't need, zeta I will be 0. Same thing in here, zeta I will be 0. But if it's a little bit, that means a little bit of error. If it's all the way to the other side, that means a lot of error. So now I have this balancing act. So the constraint here, subject to, the margin, if you remember, was WXI plus B has to be bigger than 1. That's true for both sides because Y controls the sign, is the plus or minus 1. So this would be on the plus side, would be plus 1 times this, it's at least 1. And on this side would be minus 1 times that, it's at most minus 1. But because I allow these errors, I'm putting them in there. That's how much I allow to violate that condition, right? So obviously, if I allow for some point a lot of error, I'm allowing that point instead of being a plus 1 to be all the way down here.
So is it that we set like this much amount of slack is there and the algorithm decides how much to allow for each data point?
Right. So we allow, like irregularization, a total amount of slacking. You see this sum here, right? This is a sum for I from 1 to n, all the data points. The algorithm figured out what's the right balance between rotating this plane to be in an equilibrium position, and once it's rotated, how much slack each point gets, right? Because I can rotate the plane and say these points get less slack now because it's better, but some other point got more into the margin, right? The moment I rotate the plane, I can make this point needed lower slack, but then some other point in here will need more slack, right? Depending where I choose to put this plane, some points will have bigger errors and some points will have smaller errors. We don't control who gets error. That's up to the algorithm, this optimization problem. But like irregularization, we do control how much error total we allow. This C, it's a hyperparameter, same kind you've seen in L2 regularization. That parameter there tells you how strong the regularization is, right? If I put a big regularization penalty, I'm telling my regressive classifier, I don't want high coefficients at all. I'm allowing some errors, some square loss. I'm increasing my square loss, but I really don't want high coefficients. Same thing in here. If I put a big C, what am I essentially telling this algorithm? If C becomes, plus infinity, I'm telling it I don't want slack, right? So like the more I increase C, the more this becomes a problem. So if I increase C arbitrarily high, I'm telling it I don't care about margins and W that much. I just don't want point inside my margins. I don't want slack variables. So that's achievable if the data is separable. If the data is really separable by a linear classifier, it means I can find a separation and I can lower the margins inside to the point where every point is at the margin, right? And then that means if I increase this CLI, I'm forcing the algorithm to put 0 on all the slack variables. That's only possible if the data is linearly separable, right? Because if there is a mix of pluses and minuses in the middle, no margin and no hyperplane will achieve 0 slack. But even if it's separable, if I don't put a big C in here, C is totally in my control. I decide C. It's a hyperparameter, needs tuning, needs trial and error in advance. If I don't put a big C, I'm telling the algorithm effectively, I'm allowing some slack. You have, been balancing between the W and this because it's a sum in here, right? So it's an act of balancing between those two quantities. You can have some slack if that lets you minimize the W more. So it tells it, if you can achieve a higher margin, then I'm allowing you to have some slack, right? Because that's what the thing is saying. It's saying you can have some zeta i's here that will contribute to the penalty if you can save on maximizing the margin, which is minimizing the W square. We use the square because it's easier math. who's with me? So this is important idea, not so much, support vector machines, but when you do machine learning engineering, there's often two kinds of problems. You're gonna notice when you go to industry, there's the kind of, straightforward, call an API, call a library, run a, decision tree or a regression algorithm. Stuff works, right? You're getting 96% performance, in terms of, say, classifying patients. Everybody's happy, the hospital you're happy, your boss is happy, no questions asked, right? But the problem with that is not much of a job. Anybody can do that, right? A high school graduate can download liblinear and run it, right? It's not, by now everybody can do that. So the real job of a data scientist is where stuff doesn't work that straightforward, right? I try a package, I try an SVM, I try this, boom, it doesn't work, what do I do? That's where the job is. So in those kind of cases, it's not enough to just follow an API, just call a package, and be done with it. You gotta be able to have some hook inside to say, okay, what's going on here? How do I play with this objective, or with TensorFlow, or with the regression, to try to at least understand what is my problem before I can come up with a solution. So even if you don't run SVMs, you're going to run into losses that look like this, whether it's regression or a forest or a support vector machine or some other optimization. You're going to be like, okay, the competition here is between my main objective, which is high margin, and how much errors do I allow. So I have all kinds of options here. Do I write the errors as squares? Do I write this as a square? Do I, have some other regularization, like in regression you saw that you can have two regularization terms if you want to. And now people are adding specific domain regularization. So there's L2 and L1, or in this case, the slack variables. But then for text, there's regularization with word vectors. I want similar words to have similar coefficients. That makes sense from a semantic standpoint. There is for images regularization based on whatever image detection is in these images. So that data science engineering is going to be where the job is if you want to be a data scientist. That's why I'm beating this horse here.
So on the other extreme, if we allow C, if we set C to be 0.
Right. That's a good question. What happens when C is 0? I'm saying anybody can have any amount of slack and errors as long as W gets minimized, right? So that's a ill-defined problem, because at that extreme, I can get the hyperplane with any W I want, right? Because I won't measure any error. There's effectively no constraint on where these are irrelevant constraints. If the slack variable can be any amount, then I have no real constraint in here. So I can't really go C equals 0, because that would make an ill-defined problem. But I can, balancing C versus this quantity is where the hyper parameter tuning goes, just like irregularization. All right? So that's the story, and we did some derivations, and then we said, okay, there is a duality that's going on here. So that dual problem was, we want to maximize a function of alpha, which is sum of the alpha I we did this derivation without the slack variables. I'm going to write this as a dot product here. So the dot product is xi times xj, but I'm specifically writing it in this form. So this over all ij. And I have subject to constraints. I need 0 smaller than alpha I smaller than c. That's an exercise that you have to explain exactly where this is. It's in the notes, so it's not hard to dig up where this is, but why exactly? These are the Lagrangian multipliers alpha. And the other constraint I have, which we derive, is sum of alpha I, yi equal with 0. So we did this derivation without the slack variables, but in the notes you can follow the one with slack variables if you like to. It's not difficult. Saying this is equivalent with this. What I need you to remember here is not so much the derivation. Nobody remembers the derivation. Everybody, no matter what I say, all the professors are going to look it up before the class, okay? I'm telling you. Nobody can remember this derivation. But what people do remember is the idea of duality, which is I have a saddle. Remember the saddle from last time? One way it looks this way over the horse, and the other way it looks like this so people can sit on it, right? So it's kind of concave one way, convex the other way. If you slide it across the horse, you get sections that look like that. But if you slide it perpendicular to the horse, you get sections that look like this. So there is an entire linear algebra subdomain, these Karush-Kuhn-Tucker conditions, that control in what conditions this is equivalent to this. And the equivalence geometrically comes down to that saddle point that says, if you look at all these lines sectioned out this way, and you take the minimum of all of them, the maximum of all these minimums is the saddle point. But if you cut it now the other way, you look at all these sections that are this way, everybody has a maximum. You look across the saddle at all this maximum, it took the minimum of them. That's also the saddle point. So it's saying if you optimize the problem from behind the saddle, like below the saddle, you get all these minimums, maximum of them, that's the saddle point. If you look from the top, you get all the maximums, minimum across the saddle, that's the same saddle point. That's effectively this Kernels-Kuhn-Tucker theorem, and it definitely applies for this problem. So the way support vector machines are set up, it will always apply. You don't have to worry about that. Like if you have a weird data set, Kernels-Kuhn-Tucker theorems don't apply. No, they always apply in this set. So that allows us to take the primal and dualize it. We did the derivation, but we didn't spend so much time on KKT conditions. But you saw how this comes out straight from the derivation and how there's another one that says W will be, I believe, sum of alpha I, yi, xi. So this is how you compute the plane out of the dual problem. And alpha i's were those Lagrangian multipliers, which we talked about. They correspond to tangent between two derivatives, because in a constraint optimization problem, the objective will always be tangent to the constraint at the solution. That's why we get this Lagrangian multiplier, which is the ratio between the two derivatives. So there was quite a lot of new knowledge in this whole support vector machine, right? I mean, there is the basic, can I just run this on my data and get the performance like I got with naive base? You can do that. That's what the homework is mostly, right? You can run it, get it. But there's far more math behind this than it was behind, say, a decision tree. In a decision tree, we just cut the data out to small pieces until we got to a piece that was consistent, and we say to that piece, it's always blue. And here it's far more complicated how it goes. We needed the Lagrangian multipliers. We needed duality. We need those KKT conditions, which unfortunately for the grad students have to do with how you optimize this thing. So it's not just, okay, Virgil is doing some math, you know, it's okay. It's like if you implement this, how do you solve this? We'll have to get back a little bit to the KKT conditions. Now, we're not going to ask any questions about the math, as long as you write an implementation of optimizing, of getting alphas out. That's the SMO algorithm that Bing you're going to talk about in an hour today. And it works. That's fine for the homework. But I'm going to show you before Bing talks a little bit of notes on my projector here to see exactly how much detail is in there. So this is where we are, okay? Now, we have to do two things. One thing is to talk about, okay, how do we solve this thing? In reality, big machinery, when people really were into support vector machines, like 10 years ago, everybody was so excited, a lot of prizes and awards for these support vector machines. Everybody was doing support vector machines for any problem. Now they kind of cooled off. But before, there was a vast amount of literature and implementations of support vector machines. And most of them use quadratic solvers, because this is a quadratic equation in alphas. right? You can see there's a linear term and a quadratic term. The rest are just coefficients. This is given, so this is a quadratic solver with, of course, constraints. But the constraints are linear. So that's not too bad, right, if I have linear constraints. Every one of these is kind of some line that chops my space and says you can't go on that side of the space. So mathematics have been concerned with how to solve quadratic problems before the support vector machines. We don't have to invent how to solve quadratic optimization because that's already part of math. The real issue here is to do it fast, is that it turns out from KKT conditions, if you remember, that most of these alphas will be 0. Remember? Specifically, what alphas will be 0? There's an alpha per point here. And what points will have alphas equal 0? Everything that's above, beyond my margins. Because alpha tells me the importance, the pressure on the plane the points put. And the way this is set up is that points above the margin, they don't have any influence or pressure to the plane. Only the points inside the margin or at the margin have some force that acts on the plane. So because of this, I would really want to isolate kind of quickly what points are candidates for having alphas positive. So I don't have to deal with 60,000 alphas, right? If I could somehow figure out middle way, hey, out of all those 60,000 images, here are the ones that definitely going to have alpha 0. And I still have 3,000 images or so that I'm not sure. So I would like to just set those 57,000 coefficients to 0 and just worry about the other 3,000, right? That would be much easier for my quadratic solver. So quadratic solvers are not our concern. If you run a SVM library, you're probably going to run a quadratic solver in there. And they're pretty optimized by now. It makes sense for people who do more mathematical stuff to, at some point in their math education, to take a course in optimization. And the first course is typically convex optimization, but somewhere in there you do quadratic solvers. So that's one thing that we're going to talk towards the end of the lecture. Okay, if we don't do quadratic solvers, then what? That's what you're going to have to implement. And I think everybody's familiar with coordinate ascent, which is saying keep all the coordinates fixed except one and optimize for that one, and then keep that one fixed and pick another one that's variable, and little by little optimize one of the parameters at a time. That's coordinate ascent. In here we like to do the same, except we can't just pick one. Can I say fix all the alphas and then just change one of them? Can I do that? Why not? As in increase this objective by just playing with one of them. Keep the other ones fixed.
The sum will be 0.
This sum nails the last one if everything but one is fixed, right? If you fixed all of them except one, this sum here would say the last one gotta be a certain value. So we want to do this coordinate ascent idea, but we'll pick 2, not 1. So there's 2 steps in this algorithm, which is the SMO algorithm. Very simple the way I'm going to write it here, but not so simple when you try to program it. It's a loop until it doesn't increase anymore, because my plan is to increase this stuff. I'm going to select alpha j, select a pair alpha I, alpha j. That's 2 of them. So 2. And then optimize this function in terms of the 2 that I selected, subject to the constraint. So this is easy to do, actually high school level, right? Because if I pick 2 of them, this equation will give me some sort of linear dependency between the 2, right? Suppose I pick alpha 1 and alpha 2. Either I get alpha 1 plus alpha 2 is a constant, or I get alpha 1 minus alpha 2 is a constant, depending on the y's. If the 2 alphas have the same label, plus or minus, I get the sum. If they have 1 plus 1 minus, I get the difference. Everybody can see this? If you pick any 2 alphas, doesn't have to be 1 and 2, 3 and 17. look at this, everything is fixed except for those two alphas that I picked to play with. They have a y coefficient, and I either get alpha 3 minus alpha 17 has to be a constant, or alpha 3 plus alpha 17 is going to be a constant, right? So that's that. That allows me to write one as a function of the other. If, for example, I get something like alpha 3 plus alpha 17 has to be, 12.75. I'm just inventing stuff. Then I can get one as a function of the other. That's how you would solve this system. And then if I look at this, that's a quadratic form now in alpha 3, right? Because there's going to be an alpha 3 here and an alpha 17, which is that minus alpha 3. And then it's going to be, at some point, a bunch of alpha 3s times constants, a bunch of alpha 17 times constants. But there will be one term with this alpha 3 times alpha 17, which is alpha 3 times this. So this whole thing is simply A alpha 3 squared plus B alpha 3 plus C, maximize these things. Now that I replace alpha 17 with this minus, I don't have to worry about this constraint. That's going to be satisfied for sure, because I have it right here. I only have to worry about this. This in optimization is called boxing, because everybody's bound by the same exact constraint, right? So boxing means everybody has to be in this box. So if you look at alpha 3 and alpha 17, this is 0, right? This is C somewhere here. That's C somewhere here. So it says alpha 3 and alpha 17 can get out of this box. So probably my maximum here, depending how it looks, this linear constraint is something like this. It's going to be achieved here or here. Sometimes what people do is, if under certain conditions, instead of solving the quadratic equation to find the maximum, they just compute the intercept of this line with the box and check those points to see if one of them is the solution. But nevertheless, it's not a big problem to maximize this thing. It's a simple quadratic equation of one variable, right? So you immediately take the b squared minus 4ac and figure out the solutions and done. Yes?
How do we pick this pair?
I wasn't just about to go there. So this part is pure grinding, and you're going to have some bugs and mistakes back and forth until you figure out. No problem, right? This is what he's asking. I potentially, even if I make a selection, I decided some alphas are zeros, right? I still could have potentially a lot of pairs. Let's make this simple calculation. If I have 60,000 images, and I've already got 57,000 of them, I declared those are not support vectors, so they have alpha equals 0. I still have 3,000 alphas in play. And how many pairs can I get with 3,000 alphas? Quite a lot of pairs, right? It's not feasible to try every single pair just heuristically to see if it works or not. If this optimization would be reasonably fast, gives me good progress for some pairs, and reasonably slow for most other pairs, as in points that they're close to the margin, or their alphas are already quite offset. Like once I do this, I don't change the alphas too much. I don't want to go over like on 5 million pairs to find that out. So this is something we're going to talk about at the end of the lecture today. It's actually going by a heuristic: pick one first and then pick the other. Picking the second one is relatively easy. So I'm going to give you an idea here what this is. Alpha I has to do with who's violating the KKT condition. So when I pick an alpha I, the first alpha has to do with, I look at those KKT conditions, I say, there's something off in here, they don't align yet, because the moment KKT conditions are satisfied, I'm already at the solution. So I look at who has, for example, a large alpha, but it's outside the margin. That's a violation. You can't have a non-zero alpha outside the margin. Or the other way, who looks inside the margin, but has a zero alpha. So I look at this to pick the first one. And then the second one, alpha j has to maximize some sort of energy equation, which is simple calculation. That's easier. This is all in the notes. So there'll be a two-step process. Pick the alpha I first, and then based on that alpha I, which is the best pair to pair with alpha j.
What should be the initial values of alpha?
Right? We can try something random or something more intelligent. I don't think there's a good way to initialize it. Depending on whether you start with, I mean, alphas, initial values of alpha correspond to initial value of W and B, right, effectively, because from the dual you can move back to the primal and you have a plane. So you'd like to, when you start that optimization, have a plane that's in a reasonable position, right? You can't just pick a random plane in the woods.
Instead of a plane, have you fed a curve to the
Not a plane. That's the other thing that we need to talk about today. So I'm going to do things a little bit out of order. I'm going to connect the projector to talk a little bit about these alphas. This is tedious, but it's not a lot of conceptual stuff. At the level at which we do this, it's keeping the KKT theory. Like, I do not expect you guys to go to the KKT conditions and proofs and all that. And if you don't do that, you're essentially going to have to play killer weekend of your life to get these alphas to work. Okay? The TAs will be there. They'll have already some ideas of how to choose the alphas. And again, once you choose the alphas, doing the optimization, that's straightforward. The other stuff that I need to do, we need to do to finish support vector machines, is a segue into the next topic, which is what he's asking. Okay, what if this is not a linear separation surface here? Because if I restrict this to linear problems, I won't get too far. For two reasons. Number one, data is not linearly separable. Number two, if data is linearly separable, I already have very powerful algorithms like the perceptron and even a neural network that can do a very good job. Right? I don't need all this machinery if I know data is separable. So the last big topic in this class that we want to talk about is called kernels. And they do this trick. So I'm going to start this now. We're going to stop to talk about the alphas in half an hour or so. And then next Thursday and then next week, we're going to keep talking about those kernels. So kernels, let's call it data kernels. So the informal, yes?
Very good question. So according to KKT, alphas above the margin will be 0, and alphas below the margin will be minus, right?
No, alphas are always positive.
Oh, always positive.
Okay.
Like
Alphas is a force a point pushes into the plane.
Oh,
So if it's here, it has no force. If it's here, it has some force. If it's on the other side, it has a huge force.
huge force. If it's on the margin, then still it has some force, right?
Right, but if it's outside the margin, the way the math works is basically.
Do we set the condition of the sum of alphas of positive is the sum of alphas of negative initially? Do we follow that?
This condition?
Yeah. No.
This condition is part of the dual problem. So when you solve the dual problem, you got to satisfy this. It's part of satisfiability. Alphas, in the end, have to satisfy those constraints. Now, inside the algorithm, but before you're done, what algorithm looks like to optimize is what is violated. Okay, so that's, I don't say this has to be satisfied during the algorithm at all times. I'm saying at the very end of the solution, the KKT says you gotta have this in place. It actually says more. It says that what he said, alpha will be 0 for everybody that's outside the margins and positive. In fact, will be stronger and stronger as you get closer to the plane. Points closer to the plane have a bigger force into the plane.
Where have we set the values for the slack?
The algorithm will set the values for the slack. We set only the total penalty. We set the C. Is that?
We are getting the alpha out of the SM algorithm, right?
Right, so alphas will come out of here.
Uh-huh.
What's the question?
So So where are we setting this value for the slack?
So the values for the slack will be obtained from this condition here, right?
Oh, okay.
We don't have to set them explicitly. Once we have the alphas will give us W and B. And we can look at every point and say, if it's over the one margin either way, slack is 0. And if it's inside the margin, slack has to be 1 minus that. There is a derivation, the derivation that we did from primal to dual. I have it in the notes for the slack variables. So it's of course more involved. There's more Lagrangian multipliers in there. It's not just the alphas, but I simplify the problem here. So I mean, we can go over the notes with the slack variables, not in class at all.
So if we have
I'm not gonna get to kernels. Okay.
so if we have alphas that are equal to C, are those alphas the ones that are inside the
Yes. So I think there's a homework exercise that asks you to clearly explain why it's 0 here, why it's between 0 and C on the margin, and why it's C inside when you need a slack variable. Okay. All right. So I'm going to start this kernels thing because I want to do today the discussion of how they are relevant for support vector machines. But then starting Thursday, we're going to talk only about kernels. So the easy way to think about it, kernel is a similarity function. It just tells you how similar two data points are. Very easy to understand, right? We can run domain-specific similarities. Doctors know how similar patients are, even without looking at all the lab tests. They just have this built-in accumulation of knowledge. What makes two patients similar? People who do spam filtering, they know when two emails are similar. People who do advertisement, they know when two ads are similar. Amazon knows when two products are similar. Netflix knows when two movies are similar, for whatever definition of similarity internally they have, right? So what we want is a little bit of theory of what similarity means for data. So we're going to have some theory that's concerning with what K function is a similarity. This K is going to be called a kernel. And has to have interesting algebraic properties to work with for us. But if we're going to have in practice, if we look at the primal versus dual property, like in support vector machine, what we want to is to replace this dot product xi xj right here with a different similarity function. Any kernel. Kernel again means similarity. K of xi xj. So I want to do two things. One is first understand theoretically what makes a function K a good similarity function and how to think of that conceptually. But also I would like to say that under those conditions, I can just replace, this is a dot product. Everybody knows what the dot product is, right? It's the sum of all the components, D, of xid times xjd, right? That's a dot product. Go over all the components, make the product, sum it up. First of all, that's a good kernel. So our first definition will be K of xi xj is the dot product between xi times xj. That's the basic kernel. Let's call it linear kernel. And this has all the nice properties we want. And you can see that that's already the kernel that's being used inside the support vector machine. Right? appears right there. So before we go into theory, what will mean to have this here? Suppose somebody gives me a valid kernel, satisfies all the nice properties, but it's not the dot product. Maybe it's a xi xj dot product plus 1 squared. I'm just saying. Maybe somebody verified that's a good kernel, like a valid kernel, satisfies the theory properties. I'm not worried about those now. Can I use this inside here? Like, can I just plug it in? Well, we have training and testing, right? We're still doing supervised learning. What would require to do training? You guys gonna implement SMO or somebody gonna call a quadratic solver. Can I solve this problem here, the dual problem? Not to do products, but with some function k of xi xj that's either pre-computed for me or I have an API that I can just call k of xi xj, gives me back the value. What will change in SMO? Every step I'll do will be the same, because this is a coefficient here, right? It's just this will be a different coefficient, so I can still get my alphas. That's the training part. But how do I use it for testing? Now suppose, remember who W was? That was W. If you really want to get the W and B, there was a formula for B2, right? That was my formula. So can I still do this? Is it still true? I mean, if I use a kernel instead of xi xj, will W still be this? So I need a way to do predictions, right? Once I train, I get my alphas. I'm going to say, okay, now I have a test point. I want to compute its margin, right? Because the margin will determine is it positive, is it negative, and what's my confidence. I want to be able to compute this function. So I want to compute wx plus b, right? That's what I want. So let's do this first. Let's do this first. Suppose I want to plug a kernel into SVM that is instead of xi xj dot product. The training part is the same. Use optimizer, either quadratic solver or SMO, to get the alphas. But how about testing? How do we compute? We want wx plus b for x is a test point now. That's what I need to do.
You call the kernel function on W and X.
Right, so I look at this and say, that's wx plus b. If w is that thing, that form, it will be sum of alpha I xi. This is over the training set, right? So let's call this z to be more clear. This is the z test point. Alpha I xi yi, that's w, plus times z plus b. And what happens here, I think, his observation is xi times z is effectively the dot product, which now gets replaced with the kernel value. So this will be, assuming I can compute b, I'm not going to worry about b right now. This will be sum of alpha I xi z yi for all i's in the train plus b. So now I can replace this with k of xi z. If I don't want to use dot product, I use whatever kernel. The kernel has to be consistent, of course. If I choose to use this kernel, that's going to be used everywhere. So this is to show that I can do the testing also by using the kernel in here instead of a dot product.
Won't that make evaluating each test point pretty expensive because you're going to have to compute the kernel for each test point with every training point?
Remember the alphas?
Most of them are going to be 0.
Most of them will be 0, right? So he kind of answered his question that unless I get into a weird, complicated problem that I get lost in it, I don't think I'm going to have so many values to compute, so many terms in here, number one. Number two, kernels being linear algebra functions are much faster to compute than the optimizer. Typically, the training time for SVM takes much longer than the testing because computing such values in test mode is usually much faster than this quadratic optimization doesn't go easy with linear algebra functions. Yes.
So is W still that same summation?
Not exactly, right? This I kind of wave it with magic visuals. That's what it was without the kernel. Now I don't have an explicit form unless I can factorize the kernel. So I'm going to get to that in a second. What I just showed you is I can plug in the kernel into the test mode and get classifications out of it. But his question is conceptual. Is W still this? Not if I use the kernel. But let me answer that right now. What I want for a valid kernel is to be a decomposition of a dot product. So now I'm moving to theory. Dot product. This is in a different space. So the way you should think of this, there is a mapping from the original data space into a new space. That mapping is this function v. And the kernel is simply the regular dot product into that new space. So you can think of, here's my data space, right? This is the original X. I'm moving this into a new space. Maybe this space has more dimensions. That, of course, doesn't look like more dimensions because it's still 3D, but you know what I mean, right? Yeah, so the initial data points were here. They have the x1, x2, x up to d coordinates, right? I'm moving with this transformation phi into a new space that I'm inventing new dimensions, or I change some dimensions, right? I map the data points from here to there. And in here, the kernel is simply the dot product in this space. That would be phi of xi times phi of xj dot product. So kernels are always dot products, but not in the original space of the data. The basic kernel is the dot product in the original space of the data. Any other kernel is move the data to some other space and then do the dot products. Who's with me so far? Am I answering this question? So if I have this phi function, who would this be?
Phi of xi.
Alpha I, y, phi of xi. But the magic of kernels is that we don't want to put explicitly our hands on phi. Phi could be an extremely complicated thing. What we like to work with kernels is to figure out some validity conditions, but only compute k directly. We don't want to, although conceptually k is phi times phi dot product in some weird arbitrary space, that's not how we're going to compute it. We're going to put our hands on a function k, we're going to validate that's a correct kernel, and then we don't need phi. Phi is like some hidden internal function that allows k to be a dot product, but we're never going to put our hands on phi. And that's my point here. If somebody asks me who's W, W would be in the new space now, right? Because the classification doesn't happen in the original space, it happens in the new space. I need phi, so in here W is sum of alpha I, yi, phi of xi. I would need phi to put my hands on W, but the reality is I don't want to see this space, I don't want to see phi, and I don't want to see W in it. All I want is the kernel function, which is a real value. This is a real number. Even though phi could complicate things by adding extra dimensions. So this is hard to swallow. I get it. When I heard the first time about support vector machines, I was in grad school. I'm like, damn. This is a complicated thing mathematically. And it's a complicated thing in practice too. It's not like the algorithm's easy to run. Okay? So I think you have to look at this top down. understand the main concept first, and kind of say, okay, there's a bunch of math details that are going to be worked out in here. And don't worry about those details until you get to that point, if you get to that point. Okay? So you got to understand there is a mapping that happens of the data from its original space to a new space that could easily have way more dimensions. We don't want that explicit. We don't need it explicit, although in the examples I'm going to show you, we're going to have an explicit fee. I'm going to show you what fee is. But in practice, we only need to know if the kernel, which is more like a matrix than a function, right? I mean, if you think of this kernel, what I really need is the similarity between the points in my train and test and train versus train, right? If somebody gives you matrices, this is all your similarities. All I need to know is that matrix is a valid kernel or not. That's what I need.
So with the original dot product, we computed the dot product and we got a scalar value. With the new kernel, whatever the latent phi function is, we still essentially get a different scalar value.
We get a value, a real value, but we're not going to get it by explicitly putting our hands on phi. We're going to have a function that's like this, or something like that, that doesn't tell you which phi is. There is a phi that makes this a kernel, but we don't need that phi. We only need a way to compute it based on xi and xj. So just before I connect my projector, I wanna say what makes a valid kernel. And that's the only theory I'm going to do in class. So here's what makes a valid kernel. I need two things, and you've seen these things already. K has to be symmetric as a matrix. In other words, K of xi and xj, similarity has to be the same as xj and xi. And K has to be positive semi-definite. That is for any vector V has to have the property V transpose KB is positive. So there's a theorem here that I intend to prove next time that it's simple both ways. That says if this is happening, there's gotta be a phi, which we can't put our hands on it. It's not a constructive proof. It doesn't give us phi. It just says if this is happening, there's gotta be some phi that allows K to be phi times phi in that space. And the other way, it's saying if there is such a phi, a mapping to a new space where the kernel has this property, then K must have those two properties. So in other words, this theorem saying all you need is to verify those two conditions that essentially guarantees there's some mapping into a new weird space that we don't control that will allow K to be valid. So essentially, this is what we have to check. And there is more theory that says how to construct kernels. Like if you have a kernel already, like the dot product, adding one and squaring it, it's also a valid kernel, guaranteed. So there's a bunch of techniques that says if you look at those kernels, here's how you get more kernels out of them, meaning it keeps satisfying those two properties. So we're going to talk a little bit more about this on Thursday. For now, I want to show you some examples. I think it'd be easier for me to show you with a projector.
Having two different kernels might help us to separate data which is not linearly separated.
Right. That's what I want to show you. So I think his implicit question is why use these kernels, right?
Yeah, exactly.
I mean,
Why don't they do it?
why not stick with the dot product, which is obviously easier?
Yeah, exactly.
So that's good. Let's start from there. So what did we show so far? we said, okay, if we say two things. One, make it bigger. That's not bigger. So we show two things. That if you give me a valid kernel, I can plug it in the support vector machine, right? Because I can do the training the same exact way. And in testing, I call that W x times Z dot product. I replace the dot product with whatever kernel I have, and I get the WX plus B, which is the classification score. That's my margin. I put place the point whatever I want. Everybody follows me on that? We also saw that there's some validity of those kernels. In order for them to be a dot product in some space, doesn't matter what space, they gotta have those two properties. That's a theorem I'm asking you to trust me on between now and Thursday. And the talented mathematicians can impress me by proving this by Thursday. It's easy. But then, why bother with those things, right? What they're gonna give you. So here's an example here. If I start with this, that's my original data space. Clearly, this is not linearly separable, right? Because you can look at those dots, the pluses, the circles versus the red crosses. There's no line that separates this. There's no point trying a linear separator here. It's not going to work. But what this is doing that mapping, the phi mapping. It says, if I move this from this original space, which is how many dimensions? 2. Into a space with more dimensions, I'll have to figure out those dimensions. In that space, it becomes linearly separable. So the transformation from 2D, x1, x2, right, to two coordinates, is what? x1, x2, that's the original features. And I'm adding what feature to it? Square root of 2 times x1 times x2, which is their product. If you try to do this manually by hand, you'll see that those points, even though they are kind of inside this circle, they tend to stick closer to the origin, and the other points are far away. So now in 3D, because I have my third dimension, those points being closer to the origin and the other points far away, there is a hyperplane that cuts the blue circles out of the red dots. So what did I do? I added the feature. It's not a linear transformation. Obviously it can be, right? If I just play with linear transformation like PCA, I'm never going to get this to be linearly separable. Linear transformation will only transform linear into linear, so I need something else here. I'm using this quadratic form that's a polynomial to degree 2 kernel that allows me to move the data that way. Now, is this transformation phi, how do I get the kernel out of it? Well, I use, in the new space, I use the dot product, right? So if I want the kernel between 2 points, I'll have to multiply this point representation with the other point representation. So I get what will be the x1 squared multiplies with y1 squared, that's the other point. It's a dot product, so it's plus. x2 squared multiplies with y2 squared, and square 2x1, x2 multiplies with square 2 y1, y2. So what is this? This is now, if you look at this function, what is it? Is it x1 y1 plus x2 y2 everything squared? So but how much is x1 y1 plus x2 y2? That's the dot product between x1 and x2, right? X and y. Are you guys following me?
Yeah.
This kernel, which is mapping and then doing the product, it's effectively as a function. My point is that I don't need the phi transformation to compute this kernel. This kernel in here, it's exactly, let's see, x and y like in there. It will be the dot product xy, which is x1 y1 plus x2 y2, right? Squared. So to compute the kernel, I don't need the transformation fee, and I don't need this additional feature. It has to exist conceptually, but to compute it, I just do the dot product and square it, and I get a value for my k. Remember, in my support vector machine, I don't need the fee. I only need the k's at all times. So if I have a way to compute k and guarantee that's a valid kernel, I never have to put my hands on this transformation fee function. This is just to prove that it exists and it does the right thing. But see the magic here? Data was not linearly separable, all of a sudden it is. And it doesn't change my algorithm that much, right? Because I have that k in there inside the support vector machine. The actual SMO, compute alpha, so on and so forth is pretty much the same thing. It's not like it's changing things. So people have looked at this, say, wow, that's amazing, right? Wrote a few books about it, a lot of papers, but then they say, these kernel machines, aka primal, dual, plug in a kernel that makes the data separable, even though it was not linearly separable. Can we apply it to linear regression? Wouldn't that be nice? Linear regression has the same problem. Data is not linearly separable sometimes. Can I use this machinery to kind of do some magic, the same kind of magic to regression, and get a linear classifier in a new space with a kernel? The answer is yes. Perceptron regressions, you name it. I can create from primal a dual, just like I did with the SVM, and in a dual plug in a kernel and get a regression that actually separates non-linearly separable data. That's going to be in your homework 8. How to do that with the regression function, right? So I have another example here. Same kind of examples. If I add the right features, which are listed here to give you, again, this fee here is for pedagogical purposes. In practice, we're never going to get the fee in our hands, right? And then again, what was not linearly separable out of a sudden becomes linearly separable. And then I have some other kernels that I'm going to talk about next time, which are, that's the theory about kernels. In here, what I want to point out is some classes of kernels. So there's the polynomial kernels, which are the original dot product plus a C at some power. And that will implicitly create a fee mapping that we don't want to get our hands on, but all this will be valid kernels. If I take my original dot product, add a constant raised to the power, I can prove with the theory that those will always be valid kernels. These are the polynomial kernels. Then I get the Gaussian kernels. This is a picture here of what kind of, it creates those funny regions that are non-linear across the data. If you see sometimes in demos, they run this demo and can identify any plus region with a, if you have enough data with the Gaussian kernel. So a Gaussian kernel looks like this. It's not based on the dot product. It's x minus y squared divided by a factor there, that's variance, exponential of that. We can prove that those functions satisfy the kernel properties. They are the result of some fee mapping in a high dimensional space, dot product. So we can use those without worries. There's some other, this is our optional stuff. There's some other kernels that have been tried and used in machine learning literature. The one that I would like you guys to take a look at that may be useful is this string kernel. We might talk about this in class next week. That is, how do I run a kernel for text? I have text, emails, tweets, articles. A kernel would be the similarity between those articles, right? So I don't know how, I can run the dot product, I can take the unigram matrix and just do a dot product between them. Or I can do something more interesting. This is a kernel based on n-grams. So that matching Virgil Pavlou Northeastern University in one piece of text with some other string that's based on the same words but allows some words in between. So people have developed these kernels and also tree kernels. If my data structure looks like a tree, how do I determine similarity or kernel between two trees? Every time I have a hierarchy, Those are very basic notions of kernels. So each one of them can be expanded into whatever the domain is. So people have, the last 10 years or so machine learning, been a lot of expansion into how to create those kernels. Now, kernels can make the training time slower. Is the computation of the kernel one thing, and then the selection of the alphas can come into play. Linear kernels are extremely faster than, say, polynomial RGB kernels, but I can't get linear kernels to work most of the time. In fact, people believe that whenever linear kernel works very well, you can probably just do regression and be fine with it. So the value of these support vector machines with kernels is mostly when data is not separable. So I really need to get in the kernel there to make it work.
Even if it's not separable, can you just do a regression with whatever kernel makes it separable?
Well, yeah, regression doesn't have as much power as this one. So you can plug in we'll talk about that next week. How do you plug in a kernel into regression? But it's not as powerful as this. I mean, with the expansion now of neural networks, people kind of gave up on this track in practice because neural networks can do a lot of things with those nonlinear functions. If you add layers and if you add nodes per layer, they are much more scalable in terms of computation, neural networks. We have graphics cards and now specialized hardware to do neural networks. And I think most people believe that you can't beat a neural network anyway, no matter what kernel, no matter what SVM you have. And I think the whole industry has moved away from kernels to neural networks. But before neural networks started, deep neural network really started about 2012. Before 2012, support vector machines were the bread and butter of getting machine learning jobs. Yes.
Do the algorithms also is concerned about finding the best fitting kernel, or
No,
do they do
the
it
kernel
from-
has to be, it can find the parameters. If you have a polynomial kernel of degree 3, it finds the parameters of the kernel, but you have to declare what kernel you want to use.
Oh, so I have to do trial and error which kernel
Right.
is best.
In the beginning, it's more like a data domain problem. People would know in certain, problems, Gaussian kernels are the right kernels to use. Or in certain text problems are the string kernels to use. You have to tell the algorithm which kernel you want to use. And if you download an SVM library, they'll have this option. 1 is linear kernel, 2 is degree 2 kernel, 3 is the BF kernel, the Gaussian one. They will find out the right sigmas, the right parameters of the kernel for you, but they won't change the kernel shape. That has to be inputted by the user. So if you try a degree 2 polynomial kernel, you have to tell it, I want a degree 2 polynomial kernel, and it will find out the parameters. Okay. So this is just a preview. We're going to talk a lot more about kernels, at least 2 more lectures. And we're going to move away from support vector machines. We're just going to talk about kernels and machine learning in general. There's some interesting theorems and interesting applications. Like I say, perceptrons, regressions, they can all be dualized kernels. But now, because you guys have this homework, oh, by the way, somebody asked me about this VC dimension problem for the spheres, but then that person gave up. So I digged up my proof for that one. All right. I think you did. Yeah. So I have it. Show up at office hours. We can talk about it. What I want to go over is, okay, what do we do about those alphas? That's independent of the kernel issue. Again, if we plug in a kernel, we're just changing the coefficients of that problem. It's not changing the way optimizing for alphas work, right? So this is my notes for support vector machines with a beautiful picture here that you saw it already many times, and some primality, duality. There is the slack variable formulations that you can look at. There's the kernel idea, like how you plug in a kernel, and then everything pretty much stays the same. And then once you get through all that, that's the picture. You're probably gonna take a good look for that homework exercise that tells you, explain to me the alphas. And then we have the slack variables and the SMO algorithm. I'm gonna skip the quadratic solvers. There's an entire branch of mathematics concerned with optimizations and how to do quadratic optimization. So if you run an SVM for real, you'd use that, not the SMO, Horseman, coordinate ascent, 2 at a time optimization, right? Mathematics is already quite ahead in terms of optimization and ability to deal with these problems. But what can you implement for the homework? What we want is to pick 2 of those alphas and to change just the balance between the alphas. Like I said, this condition here will impose immediately a linear constraint. If I pick alpha 3 and alpha 17, either their sum or their difference have to be constant. So I'm going to talk about the main idea here, and then Bing, you're going to demo some code for SMO, just to prove that it's possible. Okay? That's the purpose of today, is to convince everyone this is not an impossible homework. So what do? I want to set 2 of them and optimize W. Like I said, this is pretty much just calculation. Once you have the ones alpha and alpha j, solving a quadratic and getting the maximum, it's rather easy. There's some hand-drawn pictures here. Let me go to those pictures. This picture. That talks about the bounding. That if you have a linear constraint between alpha and alpha j, and you have a box, you know the alpha's gotta be in this box. One way to do it is to check where the constraint intersects the box and to check those points, because very likely the maximum you're looking for is one of those 2. That's the nature of parabolas, right? If I have a quadratic function, very likely the maximum is gonna be one of the intersection points here. So now let's go back and say, what do we actually have to do? How to optimize alpha I and alpha j, that is how to compute this function. You can follow this, but that's pretty simple to do. Again, you have to substitute alpha j in the linear form with alpha I to just stick with 1 alpha, and then you have a quadratic parabola either this way or that way. You have to see within the box where you get the maximum value. Remember, the other alphas are fixed. When you just pick alpha and alpha j, everybody else stays the same until the next iteration. So that's easy. The hard part is how to deal with selection. So as a main idea for now, I want you to break into, I need a pair alpha I, alpha j. I'm going to select alpha I first by some criteria, and then once I have alpha I, I'm going to select a pair alpha j by some other criteria. So without going into why this works, alpha I is based on the KKT conditions. Specifically the ones that we already understand, right? We know that if alpha is 0, the point has to be outside the margin, right? The margin has to be more than 1 on either side. If alpha is C, the margin has to be inside. That's your exercise for the homework. And the alpha is between 0 and C is probably a point that's supposed to be right on the dotted line, on the margin.
Why is this greater than equal to and less than equal to instead of?
You're saying if it's equal, it's supposed to be exactly between 0 and C. That's true. It's a small detail. Things in practice won't happen that exact as they happen in theory, right? The KKT conditions, while they are exact theoretically, if you have 60,000 alphas, you can't hope to really get to the point where all the alphas work the way you want, right? So this will be a small problem for you. Rather, what you want to do here is to say, which ones of those is violated the most? That's the philosophy of picking alpha I. To say, if I look at all the points, do I have something that's way outside the margin currently, but alpha is positive? Do I have something that has alpha C, but it's alpha 0 and it's way inside the margin? You're looking for strong violations of this condition, right? The pictures on the board. here too. You want to, for alpha I, look at the picture, the current picture, because presumably we have a hyperplane, and say, what seems like a strong violation of a KKT condition? That's the discrepancy between where the point is to the margin and what this current alpha is. Because the KKT conditions guarantee that when you have this balanced saddle point, you're already at the solution. So if you have no violations, you would be at the solution already. You would need to optimize nothing. So that's alpha I. Bingham and the kitchen at office hours will have more details about how to actually get it. And in here we have a little bit of more explanations. So these are notes that were put essentially by students. Once when I taught this course before, people have tried very hard to get it done, and everybody came up with, here's how I pick my alphas, here I pick my alpha J after that, and we took the solutions that work the fastest, and we updated the notes of those solutions. So there's also some internal notes that will be put on Piazza. If you get it done on your own, that's great. If not, you shouldn't spend too much time at home without help from the TA. You should come to office hours and ask, okay, what's wrong with my alpha directly, because this can take a long time. Especially because you have 3,000 choose 2 alphas. You can take a long time by choosing the wrong alphas and effectively make no progress. Okay, so back to this. That's what I want for alpha I. In here, it's elaboration on how do I look at KKT conditions and decide which ones violated the most. You probably want to skip this and get to the answer, okay, how do I pick an alpha I? The alpha J part, it's much more simpler. It's saying, if you look at the difference between the correct classification and YI, that's called the energy for a point. Once I have EI, I want the biggest difference in this E's quantity. So that's pretty easy to calculate, right? At least in principle. Once I pick one of them, I will know out of the others which one's the other one I want. But it may be a search problem. If I have 3,000 things, how many searches like that am I willing to take? Because the calculation of updating alpha and alpha J is not that hard, but the selection might take a long time to get.
What does it mean to maximize the difference of energy?
It means, so mechanically, once I have alpha I, I'm looking for the alpha J who's maximized this, I'm looking at max, right? I think what it's saying, if you look at the geometry, I want the corresponding alpha J. Once I pick my alpha I want the corresponding alpha J. That allows me for an update, right? Because I have this linear constraint, and I have to be able to make an update. If the maximum is already close to where they are right now, I'm not going to make much of an update. So I think this is saying, once you pick the alpha I, I'm going to give you something that can actually increase your objective. And then there is more calculations here that, again, I don't think you have to go through all of them, but you would have to compute the update on alpha and alpha J. We are not requiring you to finish. The TA is not going to check that your support vector machine implementation ends up with KKT conditions all satisfied. That's the solution point. But we will require a certain performance. So by the time you finish your SMO, say you do 100 rounds or so, if you are to go in test mode and use the W X plus B to classify test points, what performance you're going to get? You need a reasonably good plane. Doesn't have to be the perfect plane, but a reasonably good plane to make predictions. So that's pretty much what I have to say here. After this, there is some more theory on kernels and duality. In particular, that's high-level algebra, so that you need to take more math. It's this idea that the saddle point in here corresponds to one optimization that way and the other optimization the other way. And it's guaranteed to have this saddle point, which is a solution for both problems. Duality, it's a big deal in optimization problems. So if you were to study this from a mathematical perspective, duality is kind of the main tool for how those problems can be solved. But for us, we only need to get our hands on the alphas to be able to do classification. So I would like to ask Bingu to come here and show you his SMO. He is the one who wrote most of those notes 3 years ago. So he probably spent more time than me. What do you have there? MacBook? So here's the jack. I think this works. Is it? So I'm going to explain the SMO algorithm, and I'm going to demonstrate that it's working for your data. So in fact, this law was written like 5 years ago, 3 years ago, a long time ago. So I think we posted the algorithms online in the node. If you are interested, you can go through all the nodes to see the details. But this is the standard algorithm you should follow. If you figure out how to get your algorithm faster, that would be good. So, but this is the basic thing. So it's working, for your data. And so one tip for your implementation: don't try the large data set first. Okay, find some data, easy data, like low dimension. If I mean this, and let me show you the data when I test my code. So this is the data I'm trying. So only two classes. So and it's only 2 dimension. So try some simple data to see if your algorithm works or not. Okay, so the algorithms, so just as the Roger said, you have to pick up the alpha I first because there's a pair. So how to choose the alpha I? So alpha I is the most violate the point, which means the alpha is between 0 and C. So that's easy. So you have to, first step, you have to go through your dataset and to find out all those alpha is which is between 0 and C, and you choose them. And after that, you have to choose the alpha J, right? So the alpha J is, I think you have to choose based on this criteria. So this one is in the inner loop. So once you have the alpha I, you find the alpha J. So then you can go through all the steps from step 2 to step 8. Because this is very straightforward, and it's easy to find the violated points. So I'm going to the step 2 to step 8 to show you how to. Yeah. So in case you're lost, so make sure you write some comments. Even you go to the TA, you ask questions. Easy for people to read your code, okay, to follow your code. So the first thing, I forgot to mention that when you go through the whole data set, the alpha I should be between 0 and C, and I also violate the KKT condition. Okay, so which means the alpha is between 0 and C. It's not necessary to violate the KKT condition because the theory and the practice is different. So you have to check if it's really violate the KKT condition. And the KKT condition, there's 3 conditions here. I think in the node you can find those 3 conditions. And for each condition, you can find some easy way to see if we violate or not. So this is if else. So if this point alpha I doesn't violate the condition, you just return it. Right? Don't have to update. You don't have to check the alpha J.
How should you pick the value C?
Value C. Oh, this is a parameter. You
you have to try.
Trial and error.
Yeah, on the data set.
What would be the good initial value?
Huh?
What would be the good initial value for that?
Potential unit because
Initial value.
Initial value. Is the initial value?
Yes. Like,
Uh,
what value should I start with?
I'm not sure about because the different data set they may have a different values. So on this data set, I try some value. I can tell you on this simple data 0.6. Try.
0.6. Thanks.
Yeah. So, but I'm not sure about the SVM data set. I tried on my SVM data set. Yeah, I can show you in there, but so but it actually you can, but it's bigger than 0. Okay. You have to choose some number bigger than 0. And once you figure out if this alpha I violated the KKT condition, and you can continue this step or not. Okay. So once you choose this alpha I, you choose alpha j, which means the j has to be like a most violated point based on this formula, okay? Which is the straightforward two. And after you choose this alpha j, you have to see if the alpha j if you have to continue or not. So basically you choose alpha j, right? And you calculate the higher bound and the lower bound. And there's some details to tell you if you should continue or not. Because the most computation cost is those parts. Once you update the alpha, you have to update the OW, right? So this is the most time consuming part. So before you go to these details, you have to see if those conditions violate or not. So if like this bound is equal, so based on the load, you can see if your HF equals to L, means the alpha j won't change. So basically, the alpha j is equal to the old alpha j. So you don't have to continue, okay? Because of alpha j, if alpha j doesn't change, means the alpha I won't be changed. So that's the same thing. So and eta is the Kernel, it's the quadratic Kernel functions, and which means the alpha eta has to be bigger than 0. So this you have to check it too, because the eta is the Kernel function. Once you get the j, I, you can calculate the Kernel function and the value for the eta. So this has to be bigger than 0, and you can find this eta in the like here. Yeah. So these two kernels. It's basically it's like a square function. So which means it has to be bigger than 0. So you have to see this step. And step 4, once you check those steps conditions, for still violate these conditions, you try to calculate the real alpha j. The real alpha j is here. So you just step by step. So and once you get the alpha j, and you remember Roger show you the constraints based on those constraints. This C is a constraint. This is a box. And you once you get those alpha j, you have to click based on the H and L to get the new alpha j. So based on this condition. Back to the algorithms, which is here. Yeah. So when you get the alpha j new value, and you have to check on it based on the constraint. So this is the real new value for alpha j. Once you get the real value, you can calculate the alpha I. Before you do that, you have to check if this new alpha j, the distance is the chance is bigger than epsilon. Epsilon is another parameter. But if it's too small, which means the chance not that big, so you don't have to update alpha I. Because the alpha I, if you look at on the right side, the alpha I just the old value plus the difference. So this is the difference on the alpha j. So this part is too small. You don't have to update the alpha I. So which means you don't have to update the vi and the j. So this is basically the algorithm, and just follow these steps. And first, if you want to figure out the detail, you can read the load. And now I'm going to show you how this algorithm works. So this is the data I'm trying, right? So basically, you try to find the boundary like this green line in between these two classes. So when you run this, and remember this is a new one. I just run again. So these are boundaries. And you can try on the small data first. And when I say, and I also output the details of your code. If you remember, we try to find the violet alpha and j, right? So how could you determine your code should stop or not, right? So based on the, if you can find the violated points. So like I said, at first I go through all the data points. So on the iteration 0, I go through all the data points and to see how many alphas violate pairs. So these are pairs violated with how many alpha I and j I have to change. So 6. Once you get this alpha I and alpha j, you can put it, you know those alphas violated the condition or not, right? You can put it into the cache. So you don't have to go through all the data points again, right? Until you run out those cache points, and then you go through all data points again, so on this iteration. But between, you see, I don't have to go through all the data points. I just update the cache points, which means we only have 8 points, and we update. So this is the points, the index of the point. You can see the details, which point I update. So here I only have 100 data points, so which means every iteration I almost only update like 6 pairs or 8 pairs, like 20 points of the time. So this is 100 points. On every iteration, the out loop I only update like 7 pairs. So try only the on small data first, and also if you have any questions, go ask the TAs. And remember to write your code easier for TA to read, and because it's helping, it's going to be helpful for them to copy it. Do you guys have any questions? Yes.
You said we pick alpha I that is between 0 and C.
Yes.
But is it guaranteed that it will be, that there will be alpha I between 0 and C?
It's going to be.
I think that's how you initialize it. You look at the box and you try, I think, very hard at every alpha j to not get outside the box. If you get a little bit, like a few alphas outside the box, it's still okay. You can keep going until this is satisfied, because it's guaranteed to have a solution. The KKT conditions will always be satisfied, but you probably don't want to go that far. The violation is mostly going to be not that alphas are outside the box. The violation is going to be the discrepancy between, like I said, alpha is 0, but the point is not outside the margin. So this combination of alpha has to be sync in sync to how the constraints are happening. When you get an alpha equal 0 point something, that should be exactly on the borderline, but it's not. These are the violations that you look for to try to optimize alpha. This is going to be a lot more trial and error than the theory says for you guys. And then start talking from experience. You know, you got to make sure that when you come to the TAs, they have a way to understand what you're doing. You know, so there are variations of this algorithm. If you choose to implement some SMO that's not in the notes, that's not what the TAs have done, it's going to be very hard for them to do it. You get the credit if you do it in any way. It's just for the TAs to be able to look at them and says, what's the problem here? It's going to have to be the same person that they are using.
Yeah, so I try to draw out the support spec, the point, which is the yellow one. And as you can see, the yellow line is not really on the bottom, on the line. In practice, okay, keep little bit.
I think close enough.
Close, yeah, close enough.
Close
Because
points,
it's also
both
based on
sides.
the initialization, so you also have to be, you can say I run many times to get this good pictures, but if I run another time, maybe it's not good enough. Also, yeah, so you can see this point here, really good point, but it's really not on the point. That's it.
All right, thank you, being you.